I did not. I'm looking at what I wrote for you guys last time. Wait, what? Oh, there it is. I thought I just fixed it. I was having issues connecting to my iPad earlier, but now it's working. Okay, so this one was from last time. So you have a quiz, don't forget, next week. I don't think I wrote that down. So I'm just gonna copy this, but I'm mostly gonna change it. Copy, paste. Okay, so you have a quiz. I thought I wrote the date. Apparently I didn't. Next week. I think it's I'm not. I know when it's gonna be. I thought I told you guys earlier where it's gonna be, but I guess not. So the quiz is on 11/10 to 11/12. Oh wait, I did write that down. It's literally right there in front of my eyes. I just thought this was from the. My bad. Well, all right, whatever. I'll erase that. So that's when the quiz is at. Your third exam is going to be on chapters 5, 6, 7, and 8. Now, does anyone object? And I need confirmation. Okay? I need confirmation. So I really need you guys to pay attention to this part. Does anyone object? And you can email me, you can send me a message privately if you do. Your exam is on the 22nd, on the week of the 22nd, and you technically have 3 days, 22nd, 23rd, and 24th. However, I could extend it to the 26th, meaning you have 25 and 26. Yes, those are Thanksgiving holidays, but I'm not telling you you have to do it on the Thanksgiving holiday. That will be your choice. I'm just giving you the option if you want 2 extra days on it instead of 3.
Yes,
So
please.
does anyone object to that? If you do, send me a message saying I object to it or something. A private message will be fine, so it could be remain anonymous. I just want to make sure before I do that. Doesn't seem like it right now. I'm just trying to make sure, because then that means if everyone's cool with it or they are okay with it, I'll give you the 2 extra days. Okay, doesn't seem like nothing. Sounds good, no objections. Okay, so I'll extend it to the 26th. Because it does, I did realize that some people probably don't celebrate Thanksgiving, and that's fine. So I might as well give those 2 extra days as well, but I'm just trying to make sure. Okay, so then I guess the exam will be extended to the 26th. So you have that entire week. Okay, so you have that entire week to work on it. If you so choose to, obviously you still have a time limit, but you have that entire week. Any questions on what I just said so far? Obviously, I'm still got one more thing to add, but any questions? Okay. Now, the other thing is you do have a discussion that I'm going to post. Or maybe it's already posted. I'm not so sure, honestly. But it's going to be week 12, I believe, on your module week 12. But it's going to be on the 11/8 to the 11/14. Make sure you do this one early, and you'll see what I mean by doing it early. Obviously, you have to reply to classmates as always, but make sure you do it early, and you'll see what I mean when it's posted or when you look at it. But that one, there's your other discussion. This will most likely be your last discussion before the finals, but that's your discussion. If you have questions, let me know. Other than that, that's what it is. And then don't forget next week is Veterans Day. There's no class on Thursday. So no class for me on Thursday and no office hours because it's Veterans Day. All right, looks like we're all caught up with everything that I just said earlier. Any questions? No. Just try to make sure. All right, doesn't seem like no one has any questions. So we'll continue from what we did last time. Last time we were doing section 7.1, we didn't finish it, I believe. We left out with these two definitions. Let me copy them again. Sweet. Hopefully you guys don't have to do the exam on Thanksgiving Day, especially if you do celebrate, because then you're going to be full and trying to write it down. That might backfire on you. Or because of family, that might be the case. But just be careful when doing the exam. That's all I'm saying. It's going to be the same structure though as the last exam, where I give you a couple of questions where you have to answer. Just give me the answer and that's it. And then the other ones you will have to obviously show your work. Your final will be the same structure as well. Okay. So this is the last thing we left off with. So we're still continuing 7.1. We're going to do 7.2 as well, but this is 7.1. Okay, so last time we left off was the definition of this here, which I'm trying to remember what this definition was, the probability of the events. Oh, the probability of the event E is the sum of the probabilities of the outcomes. So S is your outcomes. Okay, so obviously P of S is a probability of the outcomes. Where S is an element of E. So all this is saying is pretty much the sum of all of these, where how many, depending on how many you have within the element. Okay. Then this term states if you have so many events, if you have technically an infinite events is a sequence of well, they don't say infinite, but they have a certain, yeah, you know what? This is an infinite sequence, an infinite one. Is a sequence of pairwise disjoint events in a sample space S, then the union of all of those, the probability of the union of all of them, because that's what this is saying, is the same thing as saying the summation of the probability of each one of those events. So that's what this is saying. So if you take the union of all of these events, how many there may be, and you find its probability, it is the same thing as finding the probability of each event independently and then adding them up. That's what that is saying. Any questions on that? I'm just trying to make sure. Okay, sweet. So now let's continue with something else on this section that we're going to talk about. Wait, is this 7.1 still or 7.2? Wait, am I off? Oh, 7.2. Oops, I thought I was in 7.1. My bad. I'm on 7.2. So this is section 7.2. So we're still doing section 7.2. Okay, sorry about that. That was confusing. Okay, so let's talk about something else on section 7.2. Definition. So let me give you the definition first. Let E and F be events with the probability of F being greater than 0. The conditional probability of E given F denoted by P of the probability of E given E vertical bar F is defined as, so the probability of E vertical bar F, and the way you read this is the probability of E given F. So that's how you will read that. The probability of E given F. That's how you read it. The probability, the conditional probability. Well, anytime you see something like this, it's a conditional probability. So the probability, the conditional probability of E given F is equal to a ratio. And on the numerator of that ratio is the probability of the intersection of those two events divided by the probability of the event F. So the probability of E given F is equal to the ratio of the intersection of those two events, the probability of the intersection of those two events, and the probability of F, the event F. This is a conditional probability. So let's do a couple examples of what I'm talking about. What is the probability of selecting a card from a 52 card deck that it is A. So obviously I'm going to give you a couple options. So that's why I wrote A. I don't know why the entire A is not showing up. There it is. What is the probability? What is the probability of selecting a card from a 52 card deck that it is a, let's say, king, given that the card is black? What is the probability of selecting a card from a 52 card deck that is a king, given that the card is black? So it's not going to say this is a conditional probability. You're going to have to determine if it's a conditional probability or not. Now, the way it's written, yes, this is a conditional probability because it's saying you want this given that. So the word given already indicates this is some type of conditional probability. So what is the probability of selecting a card from a 52 card deck that it is a king, given that the card is black? So pretty much we want a black king according to this. Okay, so one way how to do it, yes, there are other ways how to do it, but we're going to do it in terms of conditional probability is this. If we understand for a fact that this is a conditional probability. So when doing conditional probabilities, especially if you're planning on using this formula, you need to understand your events. So in this case, you have two events, event E, event F. So now the question is, what is event E? Can anyone tell me what event E is? Drawing a king, exactly. So selecting a king, good. What about event F? Okay. What about a black card? Be a little bit more specific. I know what you're trying to say, what a black card, but be a little bit more specific. Not a black king. What I was looking for is selecting a black card. Or drawing a spade or club. Yeah, that's actually good too as well, because the black cards or the the black cards, yes, the black cards in the in a 52 card deck are the clubs and the spades. Perfect. Okay, so let's say I want to find a probability of E given F. So I want a king given that is a black card. So let's figure this out. On the numerator, I want the intersection of both of these events. And on the denominator, I want just a probability of F, of the event F. So what is the probability of the intersection of both events? So what's the probability of selecting a king and a black card? Well, how many kings in a 52 card deck are black? So how many are spades and clubs? Not 26. You're right in terms of 26, something else. But how many cards are a king and a spade or a club? Two, right? There's only two. So 2 out of 52. 2 out of 52. So there's two cards that are black and a king out of 52 cards. Any questions? Okay. Now, it wouldn't be 2 out of 26, so be very careful with that. Now, what's the probability of selecting a black card? What's the probability of selecting a black card? Well, how many black cards are there in a 52 card deck? $26, right? So there's 26 out of 52 cards. So now we just have to divide this. So 2 divided by 2 over 52 divided by 26 over 52. So this is going to be just 2 divided by 26, which is the same thing as saying 1/13 or 1 over 13. You don't really have to reduce it. You could have left it as 2 over 26. That would have been fine. But that is your probability. So the probability of selecting a black card, no, selecting a king, given that is a black card, is 1 out of 13 or 2 out of 26. Good. Any questions on this? We'll do more examples, but any questions? Any questions? No? Oh, okay. Let's do another example. What if we're selecting a face card given that it is a club? I don't know what's going on with my screen sharing. Let me stop it and let me start up again. Seems to be very, very laggy. I don't like that. Yeah, it's very, very laggy today. Am I gonna have to connect? Sorry about that. Says it's connected, but it's not. This is bugging me. This is too laggy. I'm gonna have to connect it. Give me a sec. Okay. So I'm gonna connect a bit differently then. Nope, I do not have. What's going on here? What do you guys see? I don't know what you guys see right now. That's it. It's not good. If you just see my face. There it is. Wow, that took a while. Okay, now that's better. There's not much lag in it. Okay, sweet. Okay, now do you guys see the screen? Okay, sweet. Okay, a face card given that is a club. So we want to select a face card given that is a club. Well, we have two, so solution. This is clearly two events. Okay. Now, what is event E? So we have a face card given that is a club. Well, event E in this scenario will be a face card. So selecting a face card. And then F will be selecting a club. So let's figure this one out. So the probability of E given F, what does that equal? Selecting a face card and selecting a club. So again, the numerator is the probability of the intersection of both, and the denominator is a probability of F. So what is the probability of the intersection of both? So what is the probability of getting a face card and it is a club? What's the probability of getting that? Now, do you understand what I mean by the face cards? You know what are the face cards? 12 out of 52? Not quite. It has to be a face card and a club because you want it to be the intersection of both. Correct. The face cards are Jack, King, and Queen. Right. So it'll be 3 out of 52 cards. Good. Divided by the probability of getting a club. Well, there are how many clubs in a 52 card deck? 13, right? So what's the probability again of selecting a club? Because that's what we're interested in figuring out now. 13 out of 52, right? So in the end, it is, you divide these 3 out of 13, and that's pretty much it. All right, let's do another one. I'll give you one to practice on your own. C. A card whose number is less than 7, given that it is a red card. Count aces high. Now, what do I mean by high? I mean, the aces can be counted as a 1 or 11. So if I say count aces high, that means that count the ace as an 11. Okay, as numerical value will be 11. So try and do that one. I'll give you like 2 minutes. If you already know the answer, that's great, but don't type it in yet. Type it in 2 minutes. Okay, type it in 2 minutes. Aces are high, correct. So yes, you're correct about that. I can spell the word. Okay, let's see what you guys got. I don't think I gave you at all 2 minutes. I think I just barely gave you like a minute or something. But let's see what you got. Okay. So let's figure this out. So E will be selecting a card whose number is less than 7. So that means I'm looking at the set of 2, 3, 4, 5, and 6. And then F, selecting a red card. Okay. So the probability of E given F, I need the intersection of both. So 2, 4, 5, 6, 7, 2, 4, 5, 6. Selecting a red card. There are only two suits, diamonds and hearts that are red. Each suit has 13, so 26. But then we have 5 cards. So 1, 2, 3, 4, 5. So 2 of them. So 10 out of 52 that are both less than 7 and red. 10 cards that belong to that's the intersection. And selecting the red card will be 26 out of 52. So my answer is 10 out of 26. Any questions so far? Is that what everyone else got? Which if you reduce this, will be 5/13. Any questions? Okay, sweet. So now let's do something else. Definition. The events E and F are independent if and only if the intersection is the same thing as saying P of E, the intersection of both of these events. The probability of the intersection of both events is the same thing as saying the probability of event E times the probability of event F. So if this is true, if this statement is true, then the events are independent. If that is not true, the events are not independent. Okay, now what do I mean by independent events? So I'll define that. Independent events. What is that? Independent events are the occurrence of one of the events gives no information about the probability that the other event occurs. Event occurs. Or any questions on that? Any questions? Or another way of saying this, the occurrence of one event does not affect the probability of the occurrence of the other event. So for example, flipping a coin, if I flip it once, it's and I flip it again, those two events are independent. Because by flipping the coin once, it's not going to affect the probability of the next one. Does that make sense? Do I have a coin? I do not. But, no, not with me. But if I flip a coin twice, let's say I flip a coin twice. Okay, I flip it twice. The first time I flip it, it's not going to affect the second time I flip it. So those events are independent because the probability, the occurrence of the first event does not affect the probability of the other one occurring. Does not affect the probability of the other event. Okay. Now, another way you could look at it, or so what about if I select two cards? Or if let's say I want to select the ace of cards. I want to select two aces, right? Or if I select, then I have a 4 out of 52. If I want to select two cards, let's say it doesn't matter what two cards, but let's say it's an ace and a king. So let's say I want to select an ace. The probability of selecting an ace is 4 out of 52. But then you want to select a second card. Well, now what's the probability of selecting the other card? If you want to select, let's say, a king now, 4 out of 51. So notice that affects the probability. So that means that those events are not independent. If anything, those events are not independent because of the first event affected the probability of the second event. So that's a good example of not independent events. Now, let's do a couple examples of that. So let's suppose we have this. Let E and F be events that a family of two children has children. Of both sexes. And has, at most one boy, respectively. Are E and F independent? We'll do the solution here. So let E and F be events that a family of two children has children of both sexes and has at most one boy, respectively. So we have two events here, event E and event F. What is event E? Well, after reading this a couple of times, and yeah, you're going to have to read it a couple of times. Event E is a family of two children has children of both sexes. That's what event E is. Well, what about event F? Well, event F is the other one. Event F is a family of two children has at most one boy. So I want to determine if these events are independent or not. Well, let's figure it out. Let's look at E. Let's determine their events. A family of two children has children of both sexes. So what does that mean? So what are the sexes here? We're the only two sexes here. I should say that. So if a family has two children and they have children of both sexes, what are the sexes here? What are the possibilities? Right, male or female, that's it, nothing else. So it's either gonna be a girl or boy, or boy and a girl. Right? The first one could be a girl, then a boy, or the first one could be a boy and then a girl. Those are the only possibilities for this, nothing else. What about F? A family of two children has at most one boy. What are the possibilities here then? What are the possibilities here? Where G and F, I should probably write that down. G represents girl, B represents boy. So there's no confusion. So what is the set for a family of two children has at most one boy? What does that set consist of? Okay, girl, boy, boy, girl, and there's actually one more. What is that one more? Not boy, boy, because it has to be at most one boy. That's two boys. Girl, girl, perfect. Girl, girl, that's it. There's nothing else. Those are the only three possibilities. Girl, boy, boy, girl, girl, girl. Because at most one boy means one or less, meaning zero boys. So careful with the word at most and the word at least. Now, those are my events. Now to help me out too, I need my sample size. So S will be my sample size. So I kind of wanted to figure out my sample size. Well, how do I figure out my sample size here? Well, there's two kids. That's it. More, no less. Two kids. So for a family of two children, what are the only possibilities that this family can have? Well, the only possibility this family could have is two girls, the girl first and then the boy first and then the girl, or simply just two boys. There's nothing else. So these are the only possibilities. So my sample space is 4 options. That's it. Okay, so let's figure this out if these things are independent or not. So if they are independent, that means the probability of E intersect F should equal the probability of E times the probability of F. Let's see if this is true. So what's the probability of E? Well, in the probability of E, in the event E, there are only two outcomes, and there's in the sample space, there are 4 possible outcomes. So in the end, I have 2 out of 4. For the probability of F, there are 3 outcomes, and then the sample space there are 4 outcomes. So it is times 3/4. Me 6/16, or if I want to reduce it, 3/8. So I get 3/8. Perfect. Now, let's look at the probability of the intersection. Okay. So, actually, let me do this on the side so there won't be no confusion. The probability of E times the probability F. So now let's do the probability of E intersect F. Well, if I look at the intersection of both of these events, what is the intersection? How many outcomes actually intersect? Two. So 2 out of 4 outcomes intersect, which is 1/2. Are these the exact same number? No, exactly. Hence, 1/2 does not equal 3/8. So E and F are not independent. Meaning the probability of one event affects the probability of the other one. So these events are not independent. The occurrence of one event does affect the probability of the occurrence of the other event. So the occurrence of having one kid first does affect the occurrence of the second one, according to this. Well, I'm sorry. The occurrence of this event, having 2 children of different sexes, affects the probability of this event here. A family that has 2 children, but at most 1 boy. So these events are not independent. Any questions? Any questions? No? Okay, we'll do another example. Sorry. Let's try another example. Let E be the event that a randomly generated bit string of length 3 contains an odd number of ones and let F be the event that the string starts with 1 are E and F independent. So here we go. Let E be the event that randomly generated bit string of length 3 contains an odd number of ones. So I already know what my event E is. So event E is pretty much literally this. That's my event E. Sweet. Now, what is my event F? Well, they literally tell me what my event F is as well. Event F is the event that string starts with 1. So the bit string of 3, that doesn't look like a T at all. Okay. If only how you copy and paste. That's true. Okay, how do we do this? Well, I'm gonna figure out my sample space. So what is my sample space? Well, I have a bit string of length 3. So I'm gonna write all the possibilities down. 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So I think that's all of them. So here's my sample space. Now let's look at event E. Event E is a randomly generated bit string of length odd number ones. Well, if you have randomly generated string and the odd number of ones will be literally how many ones in that string. Well, you should only have 1 or 3. So there's 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 1, 1. That's what I'm thinking of. Because those are the only possibilities I could think of that have an odd number of ones. This has 1, 1, 1, 1, 1, 1, and this has 3 ones. Those are an odd number ones. F. The bit string of length 3 starts with 1. So I have 1, 1, 1, 1, 0, 1, 1, 1, 0, 1, 0, 0. Am I missing anything else? I don't think so. But that's all of them. So let's figure out if these are independent. So what's the probability of the intersection of both of these events? Okay, well, the intersection of both of these events is, well, do they have anything in common? If so, how many? Let's see, what do they have in common, if anything? I see 1 and 1 is in common with this one. Does anyone see anything else? One, 0, 0. Oh yeah, right there. So 2 of them. So I have 2 out of 8. Perfect, which is 1/4. What about the probability of E times the probability of F? Well, the probability of E is 4 out of 8. I can already tell that. The probability of F is also 4 out of 8. So this is 16 out of 64. But this is the same thing as saying 1/4. So notice that 1/4 is equal to 1/4. Hence, thus, P of the intersection of probability does equal the intersection, does equal the same thing as the product of probability of each event independently are independent. So because these are equal, it follows that E and F are independent. Okay, sweet. Now, this is actually true for any number of intersections. So it just doesn't have to be 2 events. If you have more events, let's say an n amount of events, then if all of those events are independent, if there's a pairwise, if the pairwise function, if the pairwise events are independent, then the intersection of all of them will be independent as well. So what do I mean by that? Here's the definition. The events E sub 1, E sub 2, all the way to E sub n are pairwise independent if and only if the probability of E sub I intersection E sub j is equal to P sub E sub I times the probability of E sub j for all pairs of integers I and j with I being less than j, j being less than or equal to n, but I being greater than or equal to 1. So both greater than or equal to 1. Well, one of them is greater than or equal to one is greater than or one is equal to 1. The other one has to be smaller than that. It has to be larger than. These events are mutually independent if the probability of the intersection of E sub I sub 2, all the way to the intersection of E sub I sub m equals a probability of E sub I times the probability of E sub I sub 2 times the probability of E sub I sub m whenever I sub j and j is equal to 1, 2, 3 m are integers with I sub 1 being less than I sub 2 being less than all the way to I sub m, and that being less than or equal to n, and I sub 1 being greater than or equal to 1, and m is greater than or equal to 2. Sweet. So we're going to stop here right now. Let's take a 5-minute break, and then we'll continue. We're going to finish off 7.2 and then start 7.4, which we will hopefully we finish. But we'll find out. If you have questions, let me know. Okay, let's continue. Now, let's talk let's talk about another way of finding probabilities. Okay, let's look at this term here. Theorem 7.22. The probability of exactly k successes in n independent Bernoulli trials with probability of success P and probability of failure Q, which is determined by 1 minus P, is the combination of n comma k, P raised to the k times Q raised to the n minus k. But it has to be Bernoulli trials, okay? So, a couple of notes. Bernoulli trials are experiments with only two outcomes. That's what Bernoulli trial is. There are experiments with two outcomes. Okay. Then I'll let you copy that down because I'm pretty sure you haven't copied the first part down. Okay. The experiment, here's the other condition. The experiment is repeated a fixed number of times. N times. And lastly, the probability of success remains the same for each trial. And that's what's important as well. So the probability of success cannot alter, okay? It cannot alter, it has to remain the same thing. Okay? So let's do an example of this. So you can see it. Does everyone have at least this down? I'm gonna, does everyone at least have this down? Okay, I'm assuming so. No one saying anything. So a basketball player takes 7 free throws with a probability of 0.7 of getting a basket on each shot. What is the probability of him scoring, of them, I should say, of them scoring 5 baskets? So a basketball player takes 7 free throws with a probability of 0.7 getting basket on each shot. What is the probability of them scoring 5 baskets? So is this a Bernoulli trial? Well, the events are independent. So the probability of them scoring the first shot doesn't affect the probability of them scoring the second shot. So these are independent events. Now, the probability of success, so yes, they're independent trials. It's also, there's only 2 outcomes here. So it's a Bernoulli trial because there's 2 outcomes. Either the person scores or the person does not score. That's it. Those are the only 2 possible scenarios. So they score or they not score. Okay, pretty sweet. Then we have the experiments repeated a number of times. Okay. And the probability does remain the same for each shot because they're independent events. So the probability remains the same. Okay. So let's figure it out. So the first thing you want to do is you want to find the probability of success. Well, what's the probability of success? Well, according to this, success means you're scoring a basket. So the probability of success is 0.7. Because that's what it says. Where probabilities have to add up to 1, especially if you're looking at the complements. So these will add up to 1 because the complement of success is failure. So what's the probability of this person missing? That will be 1 minus 0.7, which is 0.3. So the combination, so I know what the probability of failure is and I know what the probability of success is. So because this is a Bernoulli trial, independent events, I can use this formula here. So I'm going to do C of n comma k times p raised to the k times q raised to the n minus k. Okay. So let's do this. So C of 7 comma 5, p raised to the 0.7, 0.7 raised to the 5th power times 0.3 raised to the 5 minus, well, not 5 minus, 7 minus 5. Well, that's the same thing as saying C of 7 comma 5, 0.7 to the 5th power times 0.3 to the 2nd power. And what is that probability? Well, that's approximately 0.3176523. So the probability of this person scoring 5 baskets is about 32%. Any questions? Any questions? No? Okay. Let's try another example. A student is given a multiple choice exam. And no, you guys are not going to be given a multiple choice exam with 10 questions. Each question has 5 possible answers. Okay. The student guesses each of the answers randomly. What is the probability that this will get exactly 6 of the questions correct? So this person's obviously guessing all of them. And there's no logical reason to guess, then it's just random. Okay, I'll pick this, that's it. Out of 10 questions, what's the probability that this person will get exactly 6 correct? Well, let's think about this. Is this a Bernoulli trial? In other words, are there only 2 outcomes to this? Well, the answer is yes. There are only 2 outcomes to this. Why? Well, because the student either gets it right or the student gets it wrong. That's it. There's no order. So yes, this is a Bernoulli trial. Is it being repeated n number of times? Yes, it is. This is being repeated, well, apparently 10 times. When our scenario is actually, yeah, it's repeated 10 times. Okay. Are they independent? Yes. They're independent events. The second question doesn't, the probability of choosing the answer to the first question, the probability of choosing the answer to the second question, especially if the student's guessing randomly. Okay, so yes. Now, since that's the case, I need to determine the probability of success. probability here? And what is the probability of failure? So the probability of success. What's my probability of success here? So what is the student's probability of success? Can anyone tell me? What is the probability of success for the student? Six out of 10? Not quite. 1 out of 10? Not quite. 1 out of 5? Yes, it will be 1 out of 5. Why is it not 6 out of 10? Why is it not 1 out of 10? Because the student is guessing each question, and each question has 5 possible outcomes. So that 5 possible outcomes, out of one of those, is one of them is right. So that's why it's 1 out of 5. Now, so that means that the probability of failure is 4 out of 5, because it's 1 minus that. Okay, so let's see what this is then. So C of 10 comma 6. And then P, so it'll be 1/5 raised to the 6th power, 4/5 raised to the 10 minus 6 power. So let's determine what is this probability. Well, this is approximately 0.00550502 if you actually did it. So it's a probability of 0.5% or 0.6% that this will happen. And I'll do it again just in case. It will be a little bit higher. I guess it's because it's so many questions, or so many choices for so many questions. So I guess that does make sense. 1 divided by 5 raised to the 6, and then 4 divided by 5 raised to the 4th. Yeah, it's really small. So that's the probability of just randomly guessing. Any questions? %1 chance? Not even 1% chance. This is actually 0.6% chance. Assuming you round up, then yes, approximately 1%. But again, that's because you only have so many choices. Let's say you had 2 choices. Let's just say you had 2 choices. Like, let's say it was just true and false questions. Then the probability goes up to like 21%. So it really depends how many choices you have for each question. Let's say the question was 3 choices. So 1/3 that you have right, and there's 2/3 failure. So you have about 6% if you round up of guessing 6 of them correctly. So any questions on that? And also depends on the number of questions you have. Let's say you have way more questions. Let's say you have 50 questions. And so you're going to guess, so you've got 6 of them right, but 46 of them, no, 44 of them wrong. It's about 5%. So more questions you have, the higher percentage of guessing right. Interesting. No wonder students want so many questions on multiple choice tests. Okay, now, section 7.4. So we're done with this section. That's section 7.2. Now let's do section 7.4. Okay. Now, in order to do this section, you need a definition first. Here's the definition. This is actually from, I think, 2 sections ago, but we didn't go over it, but I'm gonna go over it now. A random variable is a function from the sample space of an experiment to the set of real numbers that is a random variable assigns a real number to each possible outcome. So let me give you a quick example of that. So random variable is not a variable and it's not random. The only reason why, and I kind of found this out from the book, I actually did not know this, that the reason why it's called like that is because there was 2 people who were arguing that how to name this thing, how to give it a specific name. And so they made a bet on what they should call it. And the person who won the bet chose random variable. And I think it was done with a flip of a coin. Like, okay, if it lands this much, if it lands tails, we're gonna call it random variable. If it lands heads, we're gonna call it this instead. So I was like, oh, that's kind of interesting. So that's why it's called a random variable, but it's not really a variable that's random or anything like that. It's actually called, it's a function. So an example that will be something like this. Let's suppose you have 2 dice, okay? And for 2 dice, you have the outcomes 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. I'm not going to write all of them down. I'm just going to write a couple. You have 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, and so on and so on, right? So let's suppose we want it to be the sum of the numbers, the sum of the dice. Well, this will give me 2. This will give me 3. This will give me 4. This will give me 5. This will give me 6. This will give me 7. This will give me 3, 4, 5, 6, 7. This will give me 8, and so on and so on and so on. So x of s could be that function, the sum of the dice. So let's say we want x is equal to 3, and it's a large x, it's not a small x. It's actually a large x. So let's say we want the probability of x is equal to 3. What that is saying is, in respect to the sum of the dice, means I want the probability of the sum of the dice to equal 3. That's what this is saying. So if I say P of X is equal to 3, I want the probability of the sum of the dice to equal to 3. So all of those that are equal to 3, how many are there, and so on. So X is equal to 3 is pretty much saying all the outcomes that add up to 3. So 1, 2, 2, 1, and I think that's it. So theoretically, I think it's 2 over 36. Its probability is 2 over 36. But the number of outcomes that have X is equal to 3 is 2 of them. 1, 2, and 2, 1. I think that's it. I don't think there's other ones that add up to 3. Yes. So, but does that make sense? That's pretty much what a random variable is. So notice that it's not really a variable that's random. But does that make sense? I don't know. Okay, I'm assuming it's yes. Okay, now I can go to this definition. The expected value also called the expectation or mean of the random variable on the sample space S. So I know which is the capital X on the sample space S, which is also capital S, is equal to E of X, which is equal to the summation, as S is an element of capital S, lowercase s, and the deviation of capital X at, I should give myself some space, at S being an element of large s, is large X of S. Actually, this is lowercase s. Let me check that one because I always forget that one actually. Yes, okay, so I was right. It was small s. Small s, oops. Minus E of, oh yeah, that makes sense. It literally says the difference between the value of large X and the mean of large X. So I'm going to give you an example. But let me write a note. Note. Expected value, another way of looking at expected value is this. This is another way of looking at it. So the expected value pretty much is this. The summation of that, the summation of the product, the summation of the product of the probability of the element and the value of the random variable at this element. Okay, that's what an expected value is. Now, another way of saying it, it is what you would expect to get in the long run. What would you expect to get in the long run? That's pretty much what an expected value is. What would you expect to get in the long run? So I'll do an example. Obviously, I'm going to do a couple examples of this so you can understand it further. So let's do an example. What is the expected value when two coins are tossed? And it pays $2 if they both show heads, but you pay $1 if one or both show tails. So suppose there's a gambling game. It always comes down to gambling when talking about probability. So suppose there's a gambling game in which you flip two coins. It pays $2 if you land on two heads. If both coins land on two heads, they both show heads. Sweet. But if there's a tails in there and the two flips, or the both tails, you pay $1. So if at least one tail shows up, you pay $1. Is it worth playing this game? Is it worth gambling? Well, one way to find out is to find the expected value. So if you play this quite often, in the long run, do you expect to benefit from it or do you expect to lose from it? That's pretty much how you're looking at this. If I gamble this and I do it, obviously I'm gonna do it a couple of times. Am I gonna win in the long run or am I gonna lose in the long run? Well, let's determine that. Okay. So let's find our sample space first. So let's determine our sample space. So we're flipping two coins. What are the possibilities? Heads, 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 tails, tails, heads, tails, tails. And these are the possibilities. Let's see my expected value. Do I not winning? Well, my expected value is a summation of the product of the probabilities of those events and the value of the random variable at that event. Lowercase s. The right lowercase s? Oh, this is supposed to be lowercase s. I'm sorry. That's supposed to be lowercase s, not big S. That's why I was getting confused. Okay. Sweet. Well, let's figure this out. Well, this is going to equal to the probability of getting two heads times x of heads, heads, plus the probability of getting tails, x of tails. And what I mean by tails here, I mean at least one tail. right? So this is one way how to look at it. So let me just write heads and then let's do this. No, actually, no, that's right. Oops. My undo button ain't working. Okay. So let's look at that. Probability of gaining heads. Well, that is simply 1/4 times, well, x of HH, there's only one of them, so 1, plus the probability of gaining tails, well, at least one tail, there's 3 of them. Wait, give me a second. Oh, gaining tails. Oh, that's why. Oops. But you know what? Let me make this a little bit better. Probably gaining heads, tails times x of HT plus the probability of gaining tails, heads times x of TH. That's why it wasn't working. Plus the probability of getting any more space. Tails. So x of TT. Well, the probability of heads, tails is 1/4. X of HT, there's only one of them, so times 1. Plus the probability of getting tails, heads is 1/4. And again, there's only one TH. And the probability of getting tails is also 1/4. And x of TT, well, there's only one of them, so times 1. So that's what we have so far. However, what we also have that's given to us is that for every time it lands at, if you have 2 heads, you get a payout of $2. But any other than that, you have to pay $1. So that means you get a payout for this one, you get a payout $2. So whatever I get, I'm going to multiply this by $2. For these, on the other hand, though, for all of them, each time you get a tails, well, I shouldn't say each time, if in the 2 flips you get a tail, you're going to pay $1. So that means you're going to multiply this by -1 because you're losing. So let's see if it's worth it. So you're going to get 2/4 minus 3/4. So you get 1/4 negative, which is negative 0.25. Oh no, we're looking at it. This is 25 cents. So in the long run, you expect to lose 25 cents a game. So is this worth it or not? Is it worth you playing this game? No, it's not. You could get lucky and you win in the first round and that'll be awesome. But in the long run, you're going to lose this game. So where people say, oh, I'm going to win the money back. Not really. It's a really small probability. In the long run, you're going to lose because that's what is expected. And and to be true, to be honest, all of these games are created so in the long run, you can lose. And it makes sense. No, 25 cents, it's a lot, especially if you do this for a number of times. In the long run, you're going to lose 25 cents per game. Now, this is how you find expected values or expected numbers, okay? This is how you do it. That's all you have to do. Now, what if you have a Bernoulli trial? Well, then that's a little bit different. Let's say for Bernoulli trials, how do you find the expected values? Well, There's a theorem for that. Theorem 7.5.2. The expected number of successes when n mutually independent Bernoulli trials are performed where P is the probability of each trial is n times P. So that's all it is, n times P. So the expected number of success when n mutually independent Bernoulli trials are performed, where P is the probability of each trial, is NP. So here's an example. Let's go back to the basketball problem, which was this one here. Where did we go? Where's the basketball one? This one here. No, not the basketball one. This is the basketball one. Copy. So let's redo this example, but I'm going to switch it. I'm going to erase this last part. What is the expected number of free throws that, let's say Lauren, let's give this person a name now, will make? So a basketball player, let's call that person Lauren. Okay. So a basketball player, Lauren, takes 7 free throws with a probability of 0.7. Sweet. Okay. Of getting a basket on each shot. What is the expected number of free throws that Lauren will make? Well, first of all, we already determined a while back ago that this is a good example of a Bernoulli trial because there's only success and failure. Lauren's either going to make it or Lauren's not going to make it. That's it. Nothing more, nothing less. So, since it's a Bernoulli trial, that means I can figure it out by just taking the probability of success, which is 0.7, and the number of free throws that Lauren is taking. And Lauren is taking, according to this, 7 free throws. Right? So if Lauren's taking 7 free throws, what is the expected number of free throws she will make, assuming she's doing this in the long run? Well, the expected value is going to be 7 times 0.07, which is a 4.9, which is approximately 5 free throws. Five free throws. Because it's really close to 5, so I might as well just round it up to 5. If you left it as 4 points, that's perfectly fine. But I'm going to leave it at 5. But that's how you find the expected number for Bernoulli trial. Any questions? Any questions? Well, the one that wasn't a Bernoulli trial was this one. This theorem only works for Bernoulli trials. Doesn't work for not Bernoulli trials. So you can't use this theorem with something that's not a Bernoulli trial. Okay. Now, let's look at another theorem. 7.5.3. If x sub I, where I is equal to 1, 2, 3, all the way to n, with n being a positive integer, are random variables on S, capital S, and if A and B are real numbers, then I is number of x sub 1 plus x sub 2 plus x sub 3 plus blah, 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 all the way x sub n is the same thing as saying the expected value of x sub 1 plus the expected value of x sub 2 plus all the way to the expected number of x sub n. So all this is saying is if you want to find the expected number of all of these random variables, the summation of these random variables is the same thing as finding the expected number of each one independently and then adding them up. And 2. An expected of ax plus b is equal to EA times E of x plus b. Okay, so let's do an example. Yes. What is the expected sum of the numbers that appear when 4 dice are rolled? Okay. What is the expected sum of the numbers that appear when 4 dice are rolled? So if I roll 4 dice, what is the sum that I would expect to come out? So if I do this in the long run, what sum do I expect to come out from all of these 4 dice? Okay. So what this is saying is this. The expectation of the expected number of x sub 1 plus x sub 2 plus x sub 3 plus x sub 4, where this represents the first die, the numbers of the second die, the numbers on the third die, and the numbers on the fourth die. And we're gonna add them all up. Now, this could take a while if we're doing it all together. I will probably have to write it out like 1, 2, like 1, 1, 1, 1, 1, 1, 1, 1, 1, 2, and so on and so on. And obviously this is gonna take a while. It's actually 6 to the 4th power. So whatever that is, I don't even know what that is actually. 6 to the 4th, that would be 1,296 possibilities or outcomes. So instead, I'm gonna use this theorem, which states if I'm doing this, it is the same, the expected number of each one of them, and then adding them up. Let's do that. So this is the same thing as expected value of x sub 1 plus the expected number of x sub 2 plus the expected number of x sub 3 plus the expected number of x sub 4. So in other words, I'm going to find the expected number of each one of these first. So let's look at one of them. Let's say the first. So let's look at the example space of our die. Well, simply going to be 1, 2, 3, 4, 5, and 6. That's it. So the expected, so the sample space for a single die is 1, 2, 3, 4, 5, 6. That's it. Okay. So the expected number of x sub 1 is equal to the probability of getting a 1 times x is equal to 1 plus the probability of getting a 2, which is times x is equal to 2, plus the probability of getting a 3, x is equal to 3, plus the probability of getting a 4 times x is equal to 4. Running out of space. Plus the probability of getting a 5, x is equal to 5, plus the probability of getting a 6. And x is equal to 6. Okay, well, the probability of getting a 1 is, well, 1, 6. 1. Plus the probability of getting a 2 is 1, 6 as well. Times when x is equal to 2, it's just 2. Plus the probability of 3 is 1, 6 times 3. 4 is 1, 4, no, 1, 6 still, times 4. Plus the probability of gain of 5 is 1, 6 times 5. Plus the probability of gain of 6 is 1, 6 times 6. So in the end, I have 1, 6 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. Well, that's simply 21 out of 6 if you actually multiply it all out and add them all up. But this is only for E, the expected number of E sub 1. So in other words, if I wrote this number in the long run, the expected, if I roll this die, I should say, if I keep rolling this die, keep rolling it over and over, the expected number that is going to come out in the long run is 21 divided by 6, which is 3.5. So approximately 4. That will be the expected number. However, the sum of rolling 4 dice. Well, since all of these are just a die, they're all going to have the same probability. So they're all going to have the exact same. Okay. The expected number of x e of x sub 1 is equal to the expected number of e of x sub 2 times the expected number of ex sub 3 and the expected number of e of x sub 4. So that means that e of x sub 1 plus x sub 2 plus x sub 3 plus x sub 4 is equal to 21 over 6 plus 21 over 6 plus 21 over 6 plus 21 over 6. So I'm going to add 21 over 6 4 times because they all die and they all have the same outcomes. So the expected numbers are going to be exactly the same. That means that this is going to be 4 times 7 over 2. That's another way of looking at it. If we reduce it by 3. So we have 28 over 2, which is equal to 14. So the expected number, or the expected sum, I should say, of the 4 dice is 14. So in the long run, if I keep rolling this die over and over, 4 dice over and over, I expect that the sums of those 4 dice will be 14 in the long run. Now, obviously, we ran out of time. We're halfway done with this section. We only need one more thing left, which we could deal with it next time. But other than that, I'll stop here. If you have questions, let me know. If not, I'll see you guys next week. Have a good weekend.
Thank you.
Bomb. Take care.